On August 24th, 2016, astronomers announced the discovery that would change everything. An Earth-sized planet orbiting in the habitable zone of Proxima Centauri, our near-stellar neighbor. The headline screamed with excitement. Our neighbor, our future, our new home. The distance, a mere 4.24 light-years. They called it close. They were catastrophically wrong. For 0.24 light-years, the number sounds almost intimate when you compare it to the vastness of space. The Andromeda Galaxy sits 2.5 million light-years away. The nearest large star cluster, the Pleiades, lies 440 light-years distant. Next to these cosmic distances, Proxima Centauri seems to sit in our backyard. This is an illusion, a dangerous illusion that masks the harsh reality of interstellar travel. For 0.24 light-years equals 40 trillion kilometers, 40 million meters, a distance so vast that human language fails to capture its true scale. If you could walk to Proxima Centauri at a steady pace of 5 kilometers per hour, never stopping, never sleeping, never resting, the journey would require 900 million years. The entire history of complex life on Earth spans only 600 million years. You would have to start walking before the first fish crawled on land. But perhaps this comparison is unfair. Humans do not walk through space. We build spacecraft. We harness technology. We achieve velocities that dwarf anything possible on foot. So let us examine what our best technology can actually accomplish. The fastest object humanity has ever created is the Parker Solar Probe. During its closest approaches to the Sun, this spacecraft achieves velocities exceeding 430,000 miles per hour. At this incomprehensible speed, the probe could circle the entire Earth in under 4 minutes. It moves so quickly that standing in New York, you could blink twice and the spacecraft would have already passed Los Angeles, continued over the Pacific Ocean, and be approaching Hawaii. This represents the absolute pinnacle of human engineering. Decades of technological development, billions of dollars in investment, the combined expertise of thousands of scientists and engineers. The Parker Solar Probe achieves its record-breaking velocity through a series of gravitational assists from Venus, stealing tiny amounts of the planet's orbital energy over years of careful trajectory adjustments. At this velocity, 430,000 miles per hour, our fastest spacecraft would require approximately 6,600 years to reach Proxima Centauri. 6,600 years. When this journey would begin, humans had not yet invented writing. The ancient Sumerians were just beginning to establish the first cities. The pyramids of Egypt would not be built for another 3,000 years. If a spacecraft had departed for Proxima Centauri when humans first developed agriculture, it would only now be approaching its destination. And this assumes the spacecraft could maintain that velocity for the entire journey, which it cannot. The Parker Solar Probe achieves its record speed only during brief perihelion passes, when gravity accelerates it around the Sun. For most of its orbit, the probe travels much slower. More importantly, it cannot sustain that velocity away from the Sun. It is trapped in solar orbit, using Venus flybys to adjust its path, but never escaping the Sun's gravitational influence entirely. For a true interstellar mission, we must consider spacecraft that can actually leave the solar system. Voyager 1, launched in 1977, currently holds the record as the most distant human-made object. After more than 47 years of continuous travel through interplanetary and now interstellar space, Voyager 1 has covered approximately 15 billion miles. This extraordinary distance, the result of nearly half a century of journey, represents less than 0.03% of the distance to Proxima Centauri. Voyager 1 travels at approximately 1,000 miles per hour relative to the Sun. At this velocity, the probe would require more than 73,000 years to reach our nearest stellar neighbor. 73,000 years. The entire span of recorded human history covers only about 5,000 years. Anatomically, modern humans have existed for perhaps 300,000 years. A Voyager 1 journey to Proxima Centauri would require nearly a quarter of the entire time our species has walked the Earth. And Voyager 1 will not survive that journey. The spacecraft carries a plutonium power source that generates electricity through radioactive decay. This power source loses approximately 4 watts per year as the plutonium depletes. By 2025, Voyager 1 will lack sufficient power to operate any scientific instruments. By 2036, it will fall silent entirely, continuing its journey as a dead artifact tumbling through the void. The probe will drift for tens of thousands of years, a monument to human ambition, never reaching any destination, never being seen again by any human eye. It will travel through the empty space between stars, covering distances that would take light years to cross, carrying its golden record of human culture to no one, to nothing, forever. Perhaps chemical rockets are simply too limited. Perhaps we need to consider more advanced propulsion concepts. Nuclear pulse propulsion, first studied seriously during Project Orion in the 1960s, offers dramatic performance improvements over chemical systems. The concept works by detonating nuclear explosives behind a massive pusher plate. Each explosion creates a plasma fireball that strikes the plate, transferring momentum to the spacecraft. Shock absorbers between the pusher plate and crew compartment smooth out the violent impulses into tolerable acceleration. Engineers conducted actual tests using conventional explosives rather than nuclear devices. They built small models with pusher plates and detonated charges beneath them, demonstrating that the concept worked in practice. The models flew. The pusher plates survived repeated blasts. The shock absorption systems functioned as designed. Nuclear test ban treaties halted the program in 1963 before atomic detonations could be tested, but the physics had been validated. Calculations showed that nuclear pulse propulsion could achieve velocities of 3 to 4% of light speed using fission bombs. Larger designs incorporating hydrogen fusion bombs could potentially reach 8 to 10% of light speed. At 10% of light speed, the journey to Proxima Centauri would require approximately 42 years. 42 years. This seems almost reasonable. A person could leave Earth in their 20s and arrive at Proxima Centauri in their 60s, potentially still vigorous enough to explore the new world. This is within the span of a human working lifetime. This is achievable. Or is it? 10% of light speed equals approximately 67 million miles per hour. Achieving this velocity requires accelerating millions of kilograms of spacecraft and payload to speeds that strain the limits of material science. The pusher plate must survive repeated exposure to nuclear fireballs at temperatures of millions of degrees. The shock absorption system must convert violent impulses into smooth acceleration without destroying the spacecraft or its occupants. The spacecraft must carry thousands of nuclear devices, each one a potential catastrophe if something goes wrong during launch or flight. Even if these engineering challenges could be solved, 42 years represents the transit time assuming constant velocity. But the spacecraft must accelerate from rest at Earth and decelerate to rest at Proxima Centauri. Nuclear pulse propulsion provides thrust, but the rocket equation still applies. You must carry fuel, and that fuel has mass, and that mass must be accelerated, requiring more fuel, which adds more mass, creating an exponential penalty. To accelerate to 10% of light speed, and then decelerate at the destination requires roughly twice the energy of one-way acceleration. The fuel mass grows accordingly. Conservative estimates suggest that a spacecraft capable of stopping at Proxima Centauri would need to be 90% fuel by mass. For every ton of useful payload, 9 tons of nuclear explosives must be carried and detonated during the journey. This is beginning to look less reasonable, but perhaps we are still thinking too conventionally. Perhaps fusion propulsion offers better performance. Project Daedalus, conducted by the British Interplanetary Society from 1973 to 1978, produced the most detailed engineering study of a fusion-powered interstellar probe. The design called for burning pellets of deuterium and helium-3 through inertial confinement fusion. Powerful electron beams would compress fuel pellets until fusion ignited, expelling the reaction products through a magnetic nozzle. Daedalus was designed to reach 12% of light speed, achieving this through a 2-stage design. The first stage would burn for 2 years, accelerating the spacecraft to 7.1% of light speed before separating. The second stage would continue acceleration for another 1.8 years, reaching final velocity. The spacecraft would coast to Barnard's star, approximately 6 light-years distant, arriving after about 50 years of flight. But Daedalus was a flyby mission. It carried no deceleration system. The spacecraft would flash through the target star system at 12% of light speed, conducting observations during its brief passage before continuing into interstellar space forever. The mission would be complete in the few days spent traversing the destination system. Everything would depend on those few days of furious data collection as the probe screamed past at 36 million miles per hour. For Proxima Centauri, even this flyby approach presents problems. 12% of light speed yields a transit time of 35 years. Add the time to build the spacecraft, perhaps a decade. Add the time for the signal carrying data to return to Earth, another 4.24 years at light speed. From project start to data reception, roughly 50 years would elapse. The scientists who designed the mission would be retired or dead before learning whether it succeeded. And this is for a robotic probe. A probe that does not need life support, does not require radiation shielding for fragile biological tissue, does not care about cosmic ray exposure or the psychological effects of decades in isolation. A probe that can be built for a one-way trip with no consideration for return. For human missions, the requirements become vastly more demanding. Humans need air, water, food. Humans need protection from radiation. Humans need space to move, exercise, maintain mental health during years or decades of confinement. Humans need a reason to survive the journey, which means they need the ability to stop at the destination, explore, and ideally return home. Every one of these requirements adds mass. Every kilogram of additional mass requires more fuel to accelerate. More fuel adds more mass, requiring even more fuel. The rocket equation's exponential tyranny becomes insurmountable. Antimatter propulsion offers the highest energy density of any fuel source. When matter and antimatter meet, they annihilate completely, converting 100% of their combined mass into energy. This compares to nuclear fission, which converts roughly 0.1% of mass to energy, and nuclear fusion, which achieves approximately 0.7% conversion. Antimatter is roughly 140 times more energy dense than fusion and 1,000 times more efficient than fission. A single gram of antimatter annihilating with a gram of normal matter releases approximately 180 trillion joules of energy. This equals the explosive yield of the Hiroshima atomic bomb. It represents the energy consumption of an average American household for 4.5 years. It could accelerate a small spacecraft to velocities that chemical rockets could never approach. An antimatter rocket could theoretically achieve 30% of light speed with reasonable fuel ratios. At this velocity, the journey to Proxima Centauri would require approximately 14 years. A crew member departing at age 25 would arrive at age 39, still young enough for decades of exploration. But there's a problem. Actually, there are several problems, and they're insurmountable with any technology we can currently envision or credibly project for development. Antimatter does not exist naturally in significant quantities anywhere in the known universe. Every antiproton used for propulsion must be manufactured through particle accelerator collisions that require enormous energy inputs. Current global antimatter production totals perhaps 10 to 20 nanograms per year, generated primarily at facilities like CERN in Switzerland and Fermilab in the United States. 10 to 20 nanograms per year. To appreciate how minuscule this production rate is, consider that an antimatter rocket might require hundreds of kilograms of antimatter fuel. At current production rates, accumulating enough antimatter for a single interstellar mission would require approximately 5 billion years. The universe itself is only 13.8 billion years old. The Sun will become a red giant and consume the Earth in about 5 billion years. We would literally need to begin production now and continue until the Earth is destroyed to accumulate sufficient fuel for one mission. The energy cost compounds this problem catastrophically. Creating antimatter through particle collisions consumes roughly 10 billion times more energy than the antimatter ultimately stores. Manufacturing enough antimatter for a single interstellar probe would require energy inputs exceeding total human civilization's power consumption for centuries or millennia. Even if we could somehow solve the production problem, storage presents equally daunting challenges. Antimatter annihilates instantly upon contact with normal matter, requiring containment systems that suspend the fuel in perfect vacuum using magnetic fields. The antimatter must never touch the container walls, must remain stable during launch vibrations, and must survive decades of storage during interstellar transit. The longest antimatter has been successfully stored is approximately 16 hours, achieved at CERN in 2023. Scaling from 16 hours to decades represents an improvement factor of roughly 10,000. Perhaps we are approaching this wrong. Perhaps instead of carrying fuel, we should push spacecraft from behind using external energy sources. Beamed energy propulsion, particularly laser-driven light sails, sidesteps the rocket equation entirely by leaving the power source at home. Breakthrough Starshot, announced in 2016 with $100 million in initial funding, represents the most serious modern effort to develop this technology. The project proposes using a ground-based laser array to accelerate tiny spacecraft called starships to 20% of light speed. At this velocity, the journey to Alpha Centauri would require approximately 20 years. The concept envisions a phased array of lasers with combined power output approaching 100 gigawatts, roughly equivalent to the electrical output of 100 large nuclear power plants. This array would focus on spacecraft massing only a few grams, consisting of a reflective sail measuring perhaps 4 meters across connected to a tiny chip carrying cameras, communication systems, and navigation equipment. The intense photon pressure would accelerate this gossamer vessel from rest to 20% of light speed in approximately 10 minutes. During those 10 minutes, the sail would experience acceleration forces exceeding 60,000 times Earth's gravity. Only the lightest possible materials could survive. Only the most miniaturized electronics could fit within the mass budget. And only a one-way flyby mission would be possible, because there is no way to slow down. This is the fatal limitation of beamed energy propulsion for human travel. A laser-propelled sail accelerates by reflecting light from behind. It cannot slow down using the same mechanism because no laser exists at the destination to push back against. A breakthrough Starshot probe would flash through the Alpha Centauri system at 20% of light speed, having mere minutes to conduct observations before departing forever into interstellar space. For robotic probes seeking photographs and spectra, this might suffice. The data will be transmitted back to Earth over 4.24 years at light speed. Scientists would receive measurements and images of another star system, an achievement of profound scientific value. But for human travelers wishing to stop, explore, establish a presence, the approach fails completely. You cannot send humans on a flyby mission that offers no possibility of deceleration. You cannot ask people to spend 20 years traveling to another star system only to pass through in minutes and continue falling through empty space forever. We are beginning to see the shape of the problem. Every propulsion concept that achieves reasonable velocities faces fatal limitations. Chemical rockets are too slow. Nuclear pulse propulsion is too dangerous and still too slow. Fusion propulsion remains theoretical and offers no deceleration option for human missions. Antimatter cannot be produced in useful quantities. Light sails cannot slow down. The fastest we can currently travel is 430,000 miles per hour, requiring 6,600 years to reach Proxima Centauri. The fastest we might plausibly achieve with near-term technology is perhaps 10 to 20% of light speed, requiring 20 to 40 years for a one-way journey with no possibility of stopping. But the tyranny of distance represents only the first barrier. Even if we could somehow solve the propulsion problem, even if we develop technology allowing spacecraft to reach significant fractions of light speed and decelerate at the destination, we would face a second barrier far more deadly than mere distance. We would face the radiation. Every second spent beyond Earth's protective magnetic field exposes spacecraft and crew to a cosmic environment that biological tissue did not evolve to tolerate. Galactic cosmic rays, high-energy particles from supernova explosions, and other violent cosmic events pervade all of space. They cannot be avoided. They cannot be shielded against effectively. They accumulate damage with every day of exposure. And Proxima Centauri adds its own deadly contribution to the radiation environment. This is not a calm, stable star like our Sun. This is a red dwarf, a class of stars known for violent stellar flares that dwarf anything our Sun produces. These flares emit torrents of X-rays and charged particles that would strip away any planetary atmosphere not protected by a strong magnetic field. Proxima b, our target destination, almost certainly has no magnetic field. The planet is likely tidally locked, showing the same face to its star at all times, just as the Moon shows the same face to Earth. Tidal locking occurs when gravitational forces synchronize a satellite's rotation period with its orbital period. For Proxima b, this means one side experiences eternal day, baked by the red dwarf's radiation, while the other side experiences eternal night, freezing in the absence of stellar heat. A tidally locked planet cannot generate a magnetic field through the same dynamo process that powers Earth's magnetosphere. Earth's field arises from convection currents in its molten iron core, driven by the planet's rotation. Without rotation, without a molten core, without the complex interplay of temperature gradients and Coriolis forces, no magnetic field emerges to shield the surface from stellar radiation. This means that any human attempting to survive on Proxima b would face the full force of stellar flares with no protection beyond whatever shielding their habitat provides. And stellar flares from red dwarfs are not gentle. A typical solar flare from our Sun releases energy equivalent to millions of hydrogen bombs. The charged particles and X-rays from such an event can disrupt satellites, damage electronics, and create beautiful auroras in Earth's polar regions. But Earth's magnetosphere deflects most of this radiation away from the surface. Life below remains protected. Proxima Centauri produces flares hundreds or thousands of times more energetic than typical solar flares. These eruptions occur regularly, sometimes multiple times per day during periods of high stellar activity. Each flare bathes the star's planets in lethal radiation. Without a magnetic field to deflect this onslaught, the surface of Proxima b receives doses that would kill exposed humans within hours or days. But we are getting ahead of ourselves. Before worrying about surface radiation at the destination, we must confront the radiation accumulated during the journey itself. A 20-year voyage to Proxima Centauri at 20% of light speed exposes crew members to continuous bombardment by galactic cosmic rays. These particles, primarily protons, but including heavier nuclei up to iron, carry enormous kinetic energy. When they strike human tissue, they do not merely deliver their energy in a single point. They create tracks of ionization through cells, breaking molecular bonds, damaging DNA, destroying cellular machinery. NASA established career radiation exposure limits decades ago based on calculations of cancer risk. These limits vary by age and sex, reflecting differences in radiation sensitivity and remaining lifespan. But all the limits cluster around 1,000 millisieverts over an entire career. Exceed this threshold, and your probability of developing radiation-induced cancer rises above what NASA considers acceptable risk. The current standard defines acceptable risk as a 3% increase in lifetime cancer mortality. This means that an astronaut who reaches their career limit faces 3 additional chances in 100 of dying from cancer, compared to an otherwise identical person who never flew in space. In deep space, beyond Earth's magnetic protection, galactic cosmic rays deliver approximately 400 to 900 millisieverts per year, depending on solar activity. Solar minimum, when the sun's magnetic field is weakest, allows more cosmic rays to penetrate the inner solar system. Solar maximum, when the sun is most active, deflects more cosmic rays but increases the risk of solar particle events. A 20-year journey to Proxima Centauri would accumulate 8,000 to 18,000 millisieverts of radiation exposure from galactic cosmic rays alone. This is 8 to 18 times NASA's career limit. This is radiation exposure that raises lifetime cancer risk by 40 to 90%. This is damage that accumulates in every cell of every organ throughout the voyage. But the numbers actually get worse, because these estimates assume modest shielding effectiveness. In practice, shielding against galactic cosmic rays presents nearly insurmountable challenges. The particles are so energetic that they pass through ordinary materials like bullets through paper. Adding more shielding helps somewhat, but thick enough shielding to provide substantial protection becomes too massive to accelerate to interstellar velocities. Worse, when high-energy particles strike shielding material, they create secondary radiation through nuclear fragmentation. The incoming cosmic ray nucleus collides with nuclei in the shield, and both shatter into smaller particles that spray outward. In some cases, thin shielding actually increases radiation dose rather than decreasing it, because the secondaries created by primary particle interactions add to the total radiation field. The optimal shielding material is hydrogen, the lightest element, which minimizes secondary particle production. Water, polyethylene, and other hydrogen-rich materials provide the best protection per unit mass. But even these materials require layers meters thick to significantly reduce cosmic ray doses. For a spacecraft that must be accelerated to 20% of light speed, carrying tens of thousands of kilograms of water shielding is simply not feasible. So the astronauts travel unprotected, or nearly so, accumulating damage throughout their voyage. The radiation does not come in a single deadly burst that kills quickly. It arrives continuously, day after day, month after month, year after year. Each cosmic ray that passes through your body creates its own microscopic track of destruction. Each heavy ion that strikes your DNA has some probability of causing mutations that survive cellular repair mechanisms. The damage accumulates. It does not heal. It does not reset. Your cells keep a running tally whether you want them to or not. By the time the spacecraft approaches Proxima Centauri after 20 years of travel, the crew has absorbed radiation doses that guarantee elevated cancer risk for the rest of their lives. But they have survived. They are alive. They have reached their destination. Now comes the next impossible problem. They must stop. A spacecraft traveling at 20% of light speed at 134 million miles per hour cannot simply apply brakes and come to rest. Slowing from this velocity requires dissipating enormous kinetic energy. The energy must go somewhere. It must be radiated away as heat, or transferred to expelled propellant, or absorbed by some mechanism that converts kinetic energy into other forms. For a light sail propelled by lasers from Earth, there is no deceleration option. The sail accelerates because photons from the laser array push against it. Once the spacecraft has traveled too far for the laser beam to remain focused, the acceleration stops. The spacecraft coasts at constant velocity. There is no way to slow down because there is no laser at the destination pushing back. Some proposals suggest using a magnetic sail for deceleration. A superconducting loop generates an enormous magnetic field that interacts with charged particles in the interstellar medium and the stellar wind at the destination. This interaction creates drag that gradually slows the spacecraft. In principle, magnetic sail deceleration works. In practice, the engineering requirements are severe. Slowing from 20% of light speed requires dissipating kinetic energy that scales with velocity squared. The magnetic field must be incredibly strong and must extend over large distances. The superconducting loop must maintain its properties despite heating from the energy dissipation. The interstellar medium must be dense enough to provide meaningful deceleration, and density varies dramatically depending on the trajectory through interstellar space. More fundamentally, magnetic sail deceleration takes time. You cannot slow from 20% of light speed to rest in days or weeks. The process might require years or decades of gradual braking. During all of this time, the crew continues absorbing cosmic ray radiation. The mission duration extends, the accumulated dose increases, and the biological cost rises accordingly. For missions using onboard propulsion, fusion, or antimatter or nuclear pulse, deceleration requires carrying fuel for the braking phase. And fuel has mass, and mass must be accelerated at the start of the journey. The rocket equation returns with brutal force. If you want to accelerate to 20% of light speed and then decelerate to rest at the destination, you need roughly twice the fuel you would need for one-way acceleration. But you must carry that deceleration fuel with you from the start, and that fuel mass must be accelerated along with everything else. The mass ratio, the ratio between initial fueled mass and final payload mass, grows exponentially. For reasonable payload fractions, for spacecraft that are not 99% fueled by mass, the achievable velocity drops precipitously when deceleration is required. A fusion rocket that might reach 20% of light speed on a flyby mission might achieve only 5 or 10% of light speed for a mission that stops at the destination. At 10% of light speed, the journey time doubles to 40 years. At 5%, it quadruples to 80 years. And throughout this extended voyage, radiation continues accumulating in crew member bodies. An 80-year mission to Proxima Centauri would deliver 32,000 to 72,000 millisieverts of radiation dose from galactic cosmic rays. This is 32 to 72 times NASA's career limit. This is radiation exposure virtually guaranteed to cause cancer. Not increased risk of cancer. Virtually certain development of radiation-induced malignancies. And we have not yet accounted for solar particle events, the sporadic bursts of radiation that occur when the Sun or Proxima Centauri produce powerful flares. These events are unpredictable and potentially lethal. A crew caught outside during a major solar particle event could receive fatal doses within hours. The Halloween storms of 2003 would have delivered approximately 2,000 millisieverts to an unprotected astronaut in interplanetary space. This dose would cause acute radiation syndrome with symptoms including nausea, vomiting, fatigue, and declining blood cell counts. Recovery would be possible but uncertain. The Carrington event of 1859, the most powerful solar storm ever recorded, would have delivered roughly 10,000 millisieverts to anyone caught outside Earth's protection. This dose would be fatal within days. Death would come from catastrophic damage to bone marrow and the gastrointestinal tract, the body's most radiation-sensitive tissues. Proxima Centauri produces flares far more energetic than the Carrington event. During periods of high activity, multiple major flares might occur per week. A crew spending months or years at Proxima B would inevitably experience multiple severe radiation events. Even with the best possible storm shelters, even with warning systems and heavily shielded compartments, the cumulative exposure would be devastating. Perhaps time dilation offers some relief. Einstein's special relativity predicts that time passes more slowly for travelers moving at high velocities relative to stationary observers. At 99% of light speed, time aboard the spacecraft flows approximately 7 times slower than time on Earth. A journey that takes 70 years from Earth's perspective occupies only 10 years of subjective time for the travelers. But time dilation requires extreme velocities to produce meaningful effects. The dilation factor, called gamma, equals 1 divided by the square root of 1 minus velocity squared divided by the speed of light squared. At low velocities, gamma barely differs from 1. At everyday speeds, time dilation is utterly negligible. At 20% of light speed, the velocity proposed for breakthrough starshot, gamma equals approximately 1.02. Time aboard the spacecraft passes about 2% slower than time on Earth. For a 20-year journey from Earth's perspective, the travelers experienced 19.6 years. They save less than 5 months of subjective time. The benefit is minimal. Even at 50% of light speed, gamma only reaches 1.15. A 20-year journey from Earth's perspective becomes 17.4 years from the traveler's perspective. You save 2.5 years of aging. Helpful, but not transformative. You need to reach 90% of light speed before time dilation becomes dramatic. At this velocity, gamma equals 2.3. A 20-year journey compresses to 8.7 years of subjective time. Now we are seeing real benefits. The travelers arrive having aged less than 9 years while Earth aged 20. But 90% of light speed is not achievable with any propulsion system we have discussed. Chemical rockets cannot approach even 1% of light speed. Nuclear pulse propulsion might reach 10%. Fusion might achieve 20%. Antimatter, if we could produce it in quantity, might reach 30 to 50%. None of these come close to 90%. To achieve 90% of light speed requires energy inputs that dwarf what any conceived propulsion system can deliver. The kinetic energy of a spacecraft at this velocity scales with gamma, which at 90% of light speed equals 2.3. You need 2.3 times more energy than Newtonian mechanics would predict. And this energy must come from somewhere. It must be carried as fuel or beamed from external sources. The amount of fuel required becomes absurd. Even with antimatter's perfect mass to energy conversion, accelerating a modest spacecraft to 90% of light speed requires antimatter mass comparable to the spacecraft's payload mass. You need 1 ton of antimatter to accelerate 1 ton of payload to this velocity. And remember, we currently produce perhaps 20 nanograms of antimatter per year globally. 1 ton equals 1 trillion nanograms. At current production rates, creating enough antimatter for a single mission would require 50 billion years. So time dilation offers no salvation. The velocities required to achieve meaningful time compression cannot be reached with any technology we can build or credibly imagine building within centuries. The travelers will experience essentially the same journey duration as observers on Earth measure. 20 years at 20% of light speed, 40 years at 10%, 80 years at 5%, every year adding to the radiation dose that accumulates in their tissues. The deceleration problem connects to another realization that mission planners rarely discuss honestly. If reaching Proxima b requires a one-way journey of decades, if the radiation exposure during transit virtually guarantees cancer and other health effects, if stopping at the destination consumes fuel that might otherwise extend mission range, then what exactly is the plan for coming home? A round-trip mission doubles everything. Double the travel time, double the radiation exposure, double the fuel mass that must be carried. If the outbound journey barely fits within the rocket equation's constraints, the return journey becomes completely impossible. Consider the mathematics. A spacecraft that can reach 20% of light speed on a one-way trip might achieve only 10% if it must carry fuel for the return journey. But 10% of light speed means 40 years each way, 80 years total travel time, plus whatever time is spent at the destination. And throughout these 80 years, radiation accumulates. 80 years of cosmic ray exposure delivers 32,000 to 72,000 millisieverts. Add another 5 or 10 years at Proxima b, exposed to stellar flares and surface radiation. Total accumulated dose could exceed 80,000 millisieverts. This is 80 times NASA's career limit. This is exposure that makes cancer not merely probable, but virtually certain, and probably multiple independent cancers developing in different organs. No one is coming home from Proxima b. The mission is one way. It has to be. The physics allows nothing else. This transforms the entire proposition. You are not asking for volunteers to visit another star system and return as heroes. You are asking for volunteers to die on another world, to spend decades in a metal coffin accumulating lethal radiation doses, to arrive at a planet that may be utterly hostile to human life, and to live out whatever brief time remains to them before cancer or other radiation-induced illnesses claim their lives. Who volunteers for this? Who looks at these numbers and says, yes, I will go? Who accepts guaranteed death in exchange for being the first human to reach another star? Perhaps someone would. History provides examples of explorers who accepted almost certain death in pursuit of discovery. The first expeditions to the poles, the first attempts to climb Everest, the first ventures into space all carried substantial mortality risk. People have always been willing to die for knowledge, for glory, for the advancement of human understanding. But those historical examples involved risks, not certainties. There was danger, yes, but also possibility of survival. Edmund Hillary and Tenzing Norgay reached the summit of Everest and returned alive. Roald Amundsen reached the South Pole and came home to tell the story. The early astronauts faced real danger, but most survived their missions. A mission to Proxima b offers no such hope. The radiation mathematics are unforgiving. You will accumulate doses that guarantee cancer. You cannot return because the fuel requirements make round trips impossible. You cannot meaningfully explore because you are dying from the moment you arrive. This is not heroic exploration. This is elaborate suicide with scientific instruments. And we have not yet addressed what awaits at the destination. We have focused on the journey, on the propulsion challenges and radiation exposure and time dilation effects. We have calculated how long it takes to reach Proxima b and what it costs in terms of human health. But we have not asked the most important question. What will they find when they arrive? Proxima b orbits in what astronomers call the habitable zone, the region around a star where liquid water could exist on a planetary surface. This definition sounds promising until you understand what it actually means. The habitable zone is defined purely by temperature, by the distance from the star, where equilibrium temperature falls between water's freezing and boiling points. That is all. Temperature. Nothing more. The habitable zone says nothing about whether the planet has an atmosphere. It says nothing about atmospheric composition. It says nothing about magnetic fields or surface conditions or radiation levels or any of the other factors that determine whether a world can actually support life. Earth orbits in the Sun's habitable zone. So does Venus, a hellscape with surface temperatures hot enough to melt lead and atmospheric pressure 90 times greater than Earth's. Mars sits at the outer edge of the habitable zone, a frozen desert with an atmosphere too thin to breathe and surface radiation levels incompatible with unprotected human presence. Being in the habitable zone means very little. It is a necessary condition for habitability, but far from sufficient. A planet must have an atmosphere of the right composition and pressure. It must have liquid water. It must have protection from stellar radiation. It must have stable surface conditions. It must have resources that could support human life or industry. Proxima b may have none of these things. We do not know. We cannot know from Earth-based observations. The planet is too small, too distant, too close to its bright star for current telescopes to characterize in detail. We can measure its mass, approximately 1.3 times Earth's mass. We can measure its orbital period, approximately 11.2 days. We can infer that it lies in the habitable zone based on the star's luminosity and the planet's orbital distance. But we cannot detect an atmosphere directly. We cannot measure surface temperature accurately. We cannot determine whether water exists in any form. We cannot assess radiation levels at the surface. Every crucial question about habitability remains unanswered. What we do know is concerning. Proxima Centauri is a red dwarf, a Class M star with peculiar properties that may make life extremely difficult for any orbiting planet. Red dwarfs are small, dim, and cool compared to yellow dwarf stars like our Sun. Their habitable zones lie very close to the star, much closer than Earth orbits the Sun. Proxima b orbits its star at a distance of approximately 0.05 astronomical units. This is about 7.5 million kilometers, roughly 1/8 the distance between Mercury and the Sun. At this proximity, tidal forces from the star are immense. These forces almost certainly locked the planet's rotation to its orbital period long ago. Tidal locking means the same hemisphere always faces the star. One side experiences perpetual day, baked by continuous stellar radiation. The other side experiences perpetual night, radiating heat into space with no input to replace it. Between these extremes lies a narrow twilight zone where conditions might be less severe. On a tidally locked planet without an atmosphere, the day side could reach temperatures exceeding several hundred degrees Celsius. The night side could plunge below -200 degrees. No liquid water could exist in either extreme. Only in the twilight zone, if at all, might temperatures permit water to remain liquid. but Proxima b likely does have an atmosphere. A planet of Earth's mass should retain atmospheric gases. The question is not whether an atmosphere exists, but what that atmosphere contains and how thick it might be. And here we encounter another problem with red dwarf stars. Red dwarfs produce powerful stellar flares with disturbing frequency. These flares emit intense bursts of X-rays and ultraviolet radiation. They accelerate charged particles to high energies. They blast into space with forces that would strip away planetary atmospheres over time unless those atmospheres are protected by strong magnetic fields. Earth's magnetic field protects our atmosphere from solar wind erosion. The magnetosphere deflects charged particles around the planet, preventing them from directly striking atmospheric gases. Without this protection, Earth would slowly lose its atmosphere to space, just as Mars has done over billions of years. Proxima b, tidally locked and likely without a magnetic field, has no such protection. Every stellar flare strips away some fraction of its atmosphere. Over millions of years, this erosion could reduce a thick atmosphere to a thin remnant, or it could remove the atmosphere entirely, leaving a barren rock exposed directly to space. If the atmosphere has been stripped away, the planet cannot support liquid water. Surface pressure would be essentially zero. Any water that once existed would have boiled into space or frozen into ice deposits in permanently shadowed craters. The habitable zone designation becomes meaningless for a world with no atmosphere. Even if the atmosphere remains, its composition is critical and entirely unknown. An atmosphere of carbon dioxide or methane or some other non-breathable gas would make the surface uninhabitable for humans without extensive life support systems. An Earth-like nitrogen-oxygen atmosphere seems unlikely for a planet exposed to constant flare bombardment, but we cannot rule it out entirely. The radiation environment adds another layer of concern. Without a magnetic field, cosmic rays and stellar wind particles strike the surface directly. Surface radiation doses on Proxima b could easily be hundreds of times higher than Earth's surface. Humans could not survive outside without substantial shielding. Any habitat would need to be buried under meters of regolith or constructed with walls thick enough to stop high-energy particles. This is not the new Earth that headlines promised. This is not a world where humans could walk outside, breathe freely, establish cities under open skies. At best, Proxima b might support a small research base, its inhabitants huddling underground while their equipment monitors the hostile environment outside. At worst, the planet is completely uninhabitable, a barren rock blasted by stellar radiation in an environment no human could survive. And remember, this is the destination. This is what awaits after 20 years of travel. After accumulating 8,000 to 18,000 millisieverts of radiation exposure, after spending decades in a spacecraft with a crew that may already be showing signs of cancer and radiation sickness, you arrive at a world that may have no breathable atmosphere. You step onto a surface that receives radiation doses incompatible with human survival. You look up at a red dwarf sun that regularly unleashes flares powerful enough to sterilize any unprotected surface. You realize that you cannot go home, cannot undo the journey, cannot escape what you have done to yourself. This is the reality that mission planners must confront when discussing human missions to Proxima b. Not the exciting possibility of reaching another star system. Not the prestige of being first. Not the scientific value of direct exploration. The reality of sending people to die on a world that probably cannot support them after a journey that guarantees their health will be destroyed. Perhaps robotic missions make more sense. Send probes that do not care about radiation. Send spacecraft that can conduct observations during high-speed flybys without needing to stop. Send machines that will never ask to come home, never question the value of their sacrifice, never regret the decision to leave Earth. Breakthrough Starshot follows exactly this logic. Tiny spacecraft, massing a few grams each, accelerated to 20% of light speed by ground-based lasers. They would flash through the Alpha Centauri system in minutes or hours, cameras recording whatever they could observe, transmitters beaming data back to Earth over 4.24 years at light speed. Some would fail. Most would fail. The harsh environment of interstellar space, the chance collisions with dust particles at relativistic velocities, the degradation of electronics over 20 years of flight, all conspire to destroy fragile spacecraft. But they are small and cheap enough to send hundreds or thousands. If even a few percent succeed, the mission is worthwhile. For robotic missions, failure is acceptable. Each spacecraft costs relatively little compared to the overall program. Launch hundreds, expect dozens to survive, hope that a few return useful data. This is how we explore hostile environments, how we probe into regions where humans cannot go, how we extend our reach beyond biological limitations. But humans cannot be sent in swarms with the expectation that most will die and a few might succeed. Each human life represents immeasurable value. Each crew member has family, friends, connections to humanity that cannot be severed lightly. The decision to send humans into interstellar space carries moral weight that robotic missions never bear. And for what? What do humans accomplish at Proxima b that robots cannot? They can make decisions in real time without waiting for signals to cross light years. They can adapt to unexpected situations with flexibility no programmed system can match. They can provide the emotional resonance, the narrative of human courage and exploration that robotic missions never generate. But these advantages must be weighed against the costs. The cost in human life and health. The cost in resources that might be spent on other endeavors. The cost in moral certainty when asking people to undertake journeys from which they cannot return. The mathematics remain unchanged by these philosophical considerations. The distance is still 4.24 light years. The journey still requires decades or more with any plausible propulsion technology. The radiation still accumulates at rates that guarantee damage. The destination still offers uncertain prospects for supporting human life. These facts are not subject to debate or optimism. They emerge from physics and biology, from the measured properties of stars and the known effects of radiation on living tissue. They describe reality, not possibility. They define what is, not what we wish could be. So we return to the question that haunts every discussion of interstellar travel. Why do we keep dreaming about Proxima b? Why do we continue planning missions we know are impossible? Why do we calculate trajectories and fuel requirements and radiation doses for journeys that will never happen? The answer lies partly in human nature, in the same impulse that drove our ancestors to cross oceans and climb mountains and venture into every unexplored corner of Earth. We are explorers by evolution. Our species survived by spreading across continents, adapting to new environments, seeking resources in unfamiliar territories. This drive to explore, to discover, to push beyond known boundaries is encoded in our psychology at levels deeper than rational calculation. Proxima b represents the ultimate expression of this drive. It is the next frontier, the nearest potentially habitable world beyond our solar system. The place that seems almost within reach if we could just solve a few technical problems. The fact that those technical problems are actually insurmountable does not diminish the appeal. If anything, the impossibility makes the goal more attractive, more worthy of the effort required to imagine how we might someday overcome these barriers. But there's also a darker motivation at work. We dream about Proxima b because we fear our future on Earth. Climate change, resource depletion, political instability, the possibility of nuclear war or pandemic or ecological collapse all drive the narrative that humanity needs a backup plan. We need somewhere else to go if Earth becomes uninhabitable. We need to spread across multiple worlds to ensure our species' survival. This motivation is understandable but fundamentally flawed. Earth, even in the worst climate scenarios, even after nuclear war, even following ecological collapse, would remain vastly more habitable than Proxima b. A post-apocalyptic Earth with runaway greenhouse warming would still have breathable atmosphere. A radiation-soaked Earth following nuclear winter would still have lower radiation levels than Proxima b's surface. A biologically devastated Earth with 90% of species extinct would still harbor more life than a tidally locked world orbiting a flare star. The idea that we should invest resources in reaching Proxima b as insurance against Earth becoming uninhabitable makes no sense when examined carefully. The resources required to establish even a minimal presence on Proxima b would dwarf the resources needed to prevent or mitigate Earth's environmental problems. If we can develop technology to survive on an alien world with no breathable atmosphere and deadly radiation, we can certainly develop technology to survive on Earth regardless of what damage we inflict. The backup planet narrative is comforting but illusory. We cannot escape Earth's problems by running to another star. We can only solve those problems here, or fail to solve them and perish. There is no escape hatch in the sky waiting to save us from our mistakes. Yet we keep dreaming. We keep calculating. We keep proposing missions that we know, intellectually, cannot succeed with current or near-term technology. Why? Perhaps because the dream itself serves a purpose independent of its feasibility. The dream of reaching Proxima b inspires us to develop better propulsion systems, more efficient energy generation, more sophisticated life support technology. These developments have value even if they never enable interstellar travel. They advance human capability in ways that benefit life on Earth. The dream also connects us to something larger than daily concerns. It reminds us that we are part of a cosmic story, that Earth is one world among trillions, that our existence here is contingent and temporary in the sweep of astronomical time. This perspective can be humbling, frightening, or inspiring depending on temperament. But it pulls our attention away from trivial conflicts toward questions of genuine significance. What is our place in the universe? Are we alone? Could life exist on other worlds? Could we ever reach those worlds? These questions have occupied human imagination for millennia. They acquire new urgency when we discover actual planets orbiting other stars, when we can point to specific worlds and say, there, that one might harbor life, that one might be reachable. Proxima b makes these abstract questions concrete. It is not a hypothetical planet in some distant galaxy. It is a real world orbiting our nearest stellar neighbor. We can observe it, though not directly. We can measure its properties, though imperfectly. We can calculate what it would take to reach it, though the answer proves discouraging. The specificity matters. General discussions about interstellar travel remain abstract, disconnected from physical reality. But when we focus on Proxima b specifically, when we calculate the exact distance and required velocity and journey time and radiation dose, the problem becomes tangible. We can grasp what is being asked of us. We can see precisely why it is impossible with current technology and what would need to change to make it possible. This clarity serves education. Students learning physics can work through the calculations themselves. How fast must a spacecraft travel to reach Proxima b in 20 years? What energy does this require? How much fuel? What radiation dose would crew members accumulate? The numbers are accessible to anyone with high school mathematics. The conclusions are unambiguous. These calculations teach not just physics, but also humility. They reveal that the universe operates according to laws that do not care about human desires. You cannot will yourself to Proxima b. You cannot reach it through determination or courage or optimism. You can only reach it by satisfying the requirements physics imposes, and those requirements are severe. The speed of light sets an absolute limit on how fast information can travel through space. This limit is not an engineering challenge waiting for clever solutions. It is a feature of space-time geometry encoded in the structure of reality. You cannot exceed it. You cannot go around it. You can only work within the constraints it imposes. Similarly, the biological effects of radiation are not negotiable. Cosmic rays damage DNA because their kinetic energy exceeds the binding energy of molecular bonds. This is chemistry and physics. It happens regardless of human wishes. You cannot develop immunity to radiation through training or genetic modification or pharmaceutical intervention. You can only reduce exposure by shielding or shorten journey times, and both approaches face fundamental limitations. The rocket equation describes the relationship between velocity, fuel, and payload. It emerges directly from conservation of momentum. You cannot violate it through creative engineering or revolutionary propulsion concepts. You can only choose which fuel to use and accept the mass ratios that choice implies. Every propulsion system, from chemical rockets to antimatter drives, must obey the rocket equation's tyranny. These physical laws feel like constraints, like barriers preventing us from achieving our goals. But they are also what makes the universe comprehensible. Without conservation laws, without consistent relationships between energy and mass and velocity, physics would be impossible. We could not predict how rockets behave or calculate journey times or estimate radiation doses. The universe would be chaos, and exploration would be futile. So the laws that make Proxima be unreachable also make it understandable. We know why it is unreachable. We can calculate exactly how unreachable it is. We can specify what would need to change, what breakthroughs would be required, what fundamental physics would need to be different for the journey to become feasible. This knowledge is valuable even if it disappoints. Better to understand our limitations than to chase impossible dreams while ignoring reality. Better to direct resources toward achievable goals than waste them on projects that physics forbids. Better to explore our solar system, which is accessible, than fixate on exoplanets that lie forever beyond reach. And our solar system offers abundant opportunities for exploration and exploitation. Mars, though cold and airless, could support research stations and possibly eventual settlement with sufficient technology. The moons of Jupiter and Saturn, particularly Europa and Enceladus and Titan, may harbor subsurface oceans that could contain life. The asteroid belt contains mineral resources exceeding anything available on Earth. These destinations are hard to reach. They require months or years of travel. They present radiation and microgravity and isolation challenges, but they are accessible with current or near-term technology. We have already sent robotic spacecraft to every planet and many smaller bodies. We have landed on Mars, on Titan, on asteroids and comets. We have collected samples and returned them to Earth. Human missions to Mars are difficult but achievable. The propulsion technology exists. The life support systems exist. The radiation exposure, while significant, falls within career limits for missions lasting a few years. The social and psychological challenges of long-duration spaceflight are surmountable with proper crew selection and mission design. Mars will never be easy to reach or comfortable to inhabit, but it is possible in ways that Proxima b simply is not. The difference is not one of degree, but of kind. Mars is hard. Proxima b is impossible. This distinction matters when allocating resources and setting priorities. Space agencies have limited budgets. They must choose between competing objectives. Money spent on speculative interstellar mission studies is money not spent on Mars program development or outer solar system exploration or Earth observation satellites or any of dozens of other valuable activities. Choosing to focus on Proxima b, to devote significant resources to planning missions that cannot happen with foreseeable technology, represents a choice to prioritize dreams over achievements. There is nothing inherently wrong with dreaming. Dreams inspire. They motivate. They push boundaries and challenge assumptions. But dreams must be balanced against practical considerations, against what can actually be accomplished with available resources. The Breakthrough Starshot Initiative, with its $100 million budget and serious technical studies, occupies a middle ground. It proposes something technically challenging but potentially achievable with sufficient engineering development. Light sails can be tested. High-power laser arrays can be built. Miniaturized electronics can be designed. None of this requires new physics or impossible breakthroughs. The mission would still be extraordinarily difficult. Most prototype spacecraft would fail. The technology readiness level for many components is low. The program would require decades of development and testing. But it is not impossible in the same way human missions to Proxima b are impossible. And even Breakthrough Starshot aims only for flyby observations. The spacecraft would pass through the Alpha Centauri system in hours, transmitting data back to Earth before continuing into interstellar space. This is valuable science. It would provide the first close-up observations of another star system. It would reveal whether Proxima b actually has an atmosphere, what that atmosphere contains, whether liquid water exists on the surface. But it is not exploration in the traditional sense. No humans would make the journey. No one would walk on alien soil or plant flags or establish permanent presence. The mission would be purely observational, a brief look at a system we can never truly visit. Is this enough? Does it satisfy the dream of reaching other stars? Or does it merely emphasize how limited our reach truly is? The answer depends on what we expect from space exploration. If the goal is knowledge, understanding the universe and our place in it, then robotic missions can succeed. Instruments do not care about radiation. Spacecraft do not need to come home. Machines can operate in environments that would kill humans within minutes or hours. Robotic exploration of the solar system has revealed worlds of astonishing diversity and beauty. The volcanoes of Io, the geysers of Enceladus, the methane lakes of Titan, the towering cliff faces of Miranda, the hexagonal storm on Saturn's North Pole. None of this required human presence. Robots discovered it all. Extending this approach to other star systems seems natural. Send robots to places too dangerous or distant for humans. Let machines brave the radiation and the decades-long journeys and the hostile environments. Bring back data that humans can analyze from the comfort and safety of Earth. But if the goal is expansion, spreading human civilization beyond its origin world, then robotic missions fail completely. Robots do not establish colonies. They do not create new societies. They do not ensure species survival through geographic distribution. For these purposes, only human presence matters, and human presence at Proxima b is not achievable. This brings us to the final calculation, the comprehensive assessment that incorporates every factor we have discussed. Let us be completely honest about what a human mission to Proxima b would require and what it would accomplish. The spacecraft must accelerate to at least 10% of light speed to make the journey time tolerably short. Slower velocities extend travel time beyond single human lifespans, creating multi-generational ship scenarios with their own severe problems. 10% of light speed requires either antimatter propulsion, which we cannot produce, or nuclear fusion propulsion, which remains undemonstrated at the required scales. Assume fusion propulsion becomes feasible. The spacecraft accelerates for several years, reaching 10% of light speed, then coasts for 40 years before beginning deceleration. Total journey time approximately 50 years outbound. Crew members in their 20s at departure would be in their 70s at arrival if they survived. During 50 years of travel, galactic cosmic rays deliver 20,000 to 45,000 millisieverts of radiation dose, even with optimal shielding. This is 20 to 45 times NASA's career limit. Every crew member would face greatly elevated cancer risk. Most would likely develop radiation-induced malignancies within years of arrival. Some would die of cancer before reaching Proxima b. The spacecraft must carry sufficient fuel for deceleration, roughly doubling the fuel mass compared to a flyby mission. This increases the initial mass that must be launched from Earth and accelerated to cruise velocity. The rocket equation's exponential penalty makes the mission barely feasible even with fusion propulsion. Small increases in required velocity or payload mass could push the design beyond what fuel ratios allow. Upon arrival, crew members must deal with an environment that is almost certainly hostile. Proxima b likely has no magnetic field, exposing the surface to stellar flares and cosmic radiation. Surface radiation doses could be hundreds of times higher than Earth levels. Any habitat must be heavily shielded, possibly buried under meters of regolith. If Proxima b has no atmosphere, or an atmosphere of unbreathable composition, the crew cannot survive outside without spacesuits. They cannot grow food in open fields under alien skies. They cannot establish a self-sufficient colony without importing vast amounts of equipment and supplies from Earth, and Earth is 50 light-years away. A signal sent requesting resupply takes 4.24 years to arrive. The response takes another 4.24 years. By the time help arrives, if it ever does, everyone who requested it would be dead. The crew cannot return to Earth. The fuel requirements for a round-trip mission are prohibitive. Even if somehow the spacecraft carried enough fuel, the return journey would take another 50 years, during which additional radiation accumulates. A crew member who left Earth at age 25 and survived the outbound journey would be 75 years old at Proxima b. They would be 125 at Earth return. No human has ever lived that long. No human with 50 years of cosmic ray exposure could possibly remain healthy enough to survive the return journey. So the mission is one way. It must be. The crew must accept that they will die at Proxima b, either from radiation-induced cancer, or from environmental hazards, or from simple old age on a world that cannot support them. They will never see Earth again. They will never reunite with family and friends. They will spend their final years or decades in isolated confinement while their bodies slowly fail from accumulated radiation damage. What do they accomplish in exchange for this sacrifice? They become the first humans to reach another star system. They collect data about Proxima b that robotic missions could gather more efficiently and safely. They plant a flag, metaphorically, claiming the world for humanity, even though humanity can never join them there. The scientific value is questionable. Anything a human crew can measure at Proxima b, a robotic mission could measure better. Robots do not need life support. They do not require radiation shielding beyond what protects their electronics. They can be built smaller and lighter, reducing fuel requirements. They can operate in conditions that would kill humans. The symbolic value exists, but serves primarily emotional needs. We want to believe humans can reach other stars. We want to feel that our species has unlimited potential. We want to believe that no distance is too great, that courage and determination can overcome any obstacle. A human mission to Proxima b would validate these beliefs, would demonstrate that we are not confined to our solar system. But validation comes at an unacceptable cost. We would be sending people to die for symbolic purposes, asking them to sacrifice everything for a goal that robotic missions could achieve without loss of life. The mathematics are clear. The biology is unforgiving. The destination offers no reasonable prospect of supporting human civilization. Some might volunteer anyway. History provides examples of people who chose death in pursuit of goals they valued above survival. Religious martyrs, political revolutionaries, soldiers defending hopeless positions, all faced certain death for causes they believed justified the sacrifice. Perhaps some would view reaching Proxima b as worthy of similar commitment. But should we accept such volunteers? Should we build a mission designed to kill its crew? Should we invest resources in sending humans to die when robots could accomplish the same objectives without casualties? These are not technical questions. They are moral questions that transcend physics and engineering. They force us to examine what we value, what we are willing to sacrifice, what purposes justify the loss of human life. The answers are not obvious and certainly not universal. Different cultures, different ethical frameworks, different individuals would answer differently. Some would say no reasonable goal justifies sending people on suicide missions. Others would argue that individuals have the right to choose their own risks, to volunteer for dangerous endeavors even when the danger amounts to certainty of death. The debate matters because it reveals assumptions about human worth and purpose. If we believe each human life has intrinsic value that cannot be reduced to instrumental purposes, then missions designed to kill their crews are unacceptable regardless of what they accomplish. If we believe humans have the right to determine their own fates, to accept whatever risks they choose in pursuit of goals they value, then such missions might be permissible given informed consent. I cannot resolve this debate. Different readers will reach different conclusions based on their values and beliefs. But the debate must happen. We must confront these questions honestly before committing resources to human interstellar missions. We must decide what we are willing to accept and what crosses ethical boundaries that should not be crossed. What I can say with certainty is that the physics and biology are unforgiving. Proxima b is not a welcoming destination. The journey cannot be made safely with current or foreseeable technology. The crew would suffer radiation damage that guarantees health problems and early death. The destination likely cannot support human life without extensive technological intervention. Return is impossible. These facts are not subject to debate or optimism. The harsh reality is that Proxima b might as well be in another universe. The 4.24 light-years that separate us from our nearest exoplanet represent not merely distance, but impossibility. We can see the world through telescopes. We can measure its properties and calculate its orbit and estimate its climate. But we cannot reach it. We cannot touch it. We cannot walk on its surface or breathe its air or establish cities under its sky. The universe has drawn a boundary around humanity, a limit beyond which our biological nature prevents expansion. That boundary lies somewhere between Mars, which is difficult but possible, and Proxima b, which is impossible. We can send our instruments and our robots beyond this boundary. We can observe and measure and learn, but we cannot follow. This limitation is not temporary. It is not something that future technology will solve through sufficient cleverness and investment. The barriers are fundamental, woven into the structure of space-time and the biochemistry of life. Breaking through would require not incremental improvements, but revolutionary changes in physics that seem unlikely to ever occur. Perhaps in centuries or millennia, physics will reveal new phenomena that enable faster than light travel or perfect radiation shielding or some other breakthrough that makes interstellar human missions feasible. Perhaps future humans will develop technology so advanced that current limitations become irrelevant. Perhaps biological humans will be replaced by synthetic or heavily modified forms, less vulnerable to radiation and time. These possibilities exist in the realm of speculation, not engineering. They require either unknown physics or transformations of human nature so profound that the beings who travel to Proxima b would not really be us in any meaningful sense. Hoping for such breakthroughs is not a plan. It is fantasy, so we are left with the reality we inhabit. Earth is our home. Our solar system is our neighborhood. Proxima b and every other exoplanet lie beyond reach. We can dream about them. We can study them from afar. We can send robots to investigate if we develop the technology. But we cannot go ourselves. This conclusion disappoints. It contradicts the narrative of unlimited human potential that pervades our culture. It suggests there are hard limits on what we can accomplish, boundaries we cannot cross through effort or ingenuity. It implies that the universe is larger and harsher than our myths admit. But it is also liberating in its own way. If Proxima b is unreachable, we can stop pretending otherwise. We can stop wasting resources on plans that will never come to fruition. We can redirect attention and investment toward goals that are actually achievable. We can focus on Mars, on the outer solar system, on robotic exploration, on understanding and preserving Earth. We can accept that humanity is bound to its origin system, at least for the foreseeable future and probably forever. This is not defeat. This is clarity. We know where we can go and where we cannot. We understand the limits physics imposes. We can work within those limits to accomplish extraordinary things without chasing impossible dreams. Our solar system offers room for growth and exploration that will occupy humanity for centuries at minimum. 8 planets, hundreds of moons, millions of asteroids, countless comets, all waiting to be studied and potentially exploited. Some may harbor life. Some may contain resources that enable expansion beyond Earth. Some may reveal secrets about planetary formation, solar system evolution, the origins of life itself. These are real destinations with real potential. They are hard to reach, but not impossible. They require technology we can build and missions we can afford. They allow humans to expand beyond Earth without asking them to sacrifice their lives or accept certain death from radiation exposure. Proxima b will always be there, shining faintly in the sky, reminding us of worlds beyond our reach. We can observe it with increasingly sophisticated telescopes. We can refine our measurements of its mass and orbit and possibly its atmosphere. We can learn whether it truly harbors conditions suitable for life. We can study it intensely while accepting we will never visit. This is enough. It has to be. The universe does not care what we want. Physics operates according to laws that feel no compassion for human dreams. The distance to Proxima b, for 0.24 light-years, 40 trillion kilometers, represents an impassable gulf that no amount of determination can bridge. We are here. Proxima b is there. The space between is too vast, too hostile, too fundamentally incompatible with biological life for any journey to succeed. This is the harsh reality we must accept. The dream was beautiful while it lasted. The vision of humans walking on the surface of Proxima b, establishing colonies around other stars, spreading across the galaxy like we once spread across Earth. This vision inspired generations and drove technological development and gave purpose to countless hours of research and planning. But it was always fantasy. The numbers never worked. The biology never permitted it. The physics never allowed it. We wanted it to be possible so badly that we ignored the evidence, overlooked the impossible requirements, convinced ourselves that future breakthroughs would solve problems that have no solutions. Now we must wake up. We must see Proxima b for what it truly is, not our future home, but our cosmic neighbor forever separated from us by a distance we cannot cross. We must redirect our dreams toward destinations we can actually reach, goals we can truly accomplish, futures we can realistically build. This is not giving up. This is growing up. This is accepting reality and working within its constraints rather than raging against limits we cannot change. This is choosing to invest our resources wisely, to pursue achievable goals, to build a future in our solar system rather than fixating on fantasies of interstellar empires. Every night, you can step outside and look up at Alpha Centauri. You can see it with your naked eye, a single point of light holding 3 stars in gravitational embrace. Proxima Centauri is there too dim to see directly, but orbiting its brighter companions at great distance. And orbiting Proxima Centauri is Proxima b, the closest potentially habitable planet to Earth. For 0.24 light-years away, 40 trillion kilometers, the nearest exoplanet we have ever found. And it might as well be on the other side of infinity. The physics forbids it. The biology forbids it. The mathematics forbid it. We can dream. We can plan. We can calculate. We can hope that someday, somehow, the universe will reveal a loophole we have not yet discovered, a way around the barriers that currently seem insurmountable. But we cannot go. Not now, not soon, and probably not ever. Proxima b is not our future. It is our limit. It is the boundary that separates what is possible from what is not, what we can achieve from what we can only observe, where we can travel from where we can only dream of traveling. And limits, unlike dreams, are absolute. The universe has spoken. The distance is too great. The radiation is too severe. The journey is too long. The destination is too hostile. The return is impossible. The cost in human life and health exceeds any benefit the mission could provide. This is the harsh reality. This is why it is impossible to reach Proxima b. Not difficult, not expensive, not dangerous in ways that courage might overcome. Impossible. Simply, completely, irrevocably impossible. The dream is over. It is time to wake up. But perhaps we should examine this conclusion more carefully. Perhaps dismissing Proxima b as completely impossible oversimplifies the situation. Let us consider what advances in technology, what changes in human capability, what transformations in our approach to space exploration might shift the equation, even slightly. The radiation problem is severe, yes, but it is not binary. Radiation exposure does not instantly kill at threshold doses. It increases cancer risk probabilistically. A crew that receives 20,000 millisieverts has perhaps an 80% chance of developing radiation-induced cancer within their lifetime, not a 100% guarantee of immediate death. Some individuals might survive the journey, arrive at Proxima b, and live for decades before any malignancy develops. Should we reject the entire proposition because most crew members will eventually develop cancer? Mountaineers climbing Everest face mortality rates exceeding 10% on some routes. Deep-sea fishermen work jobs with fatality rates far higher than most professions. Test pilots in the early jet age knew that crashes killed colleagues regularly. Yet people volunteered for these endeavors, accepting risks that would be unthinkable in ordinary circumstances. If volunteers understood the radiation risks completely, if they gave informed consent knowing that cancer was probable and return was impossible, would their choice be valid? Would we have the moral authority to prevent them from going? The question becomes more complex when we consider that some crew members might value the mission above their own longevity. A scientist given the opportunity to study Proxima b firsthand might willingly trade 20 years of retirement for the chance to walk on another world. An explorer driven by the same impulses that sent humans across oceans and over mountains might view early death from radiation-induced cancer as acceptable payment for reaching another star. We cannot dismiss these perspectives as irrational or uninformed. People make choices that prioritize meaning over survival constantly. Soldiers volunteer for combat. Aid workers travel to war zones and epidemic regions. Researchers study dangerous organisms and toxic chemicals. The notion that life extension should always trump other values is itself a value judgment, not an objective truth. So perhaps the radiation barrier is permeable in ways that pure statistics suggest, not because the physics changes, but because human values and choices are more complex than dose calculations capture. This does not make the mission safe or advisable. It merely acknowledges that impossibility has degrees, that absolute pronouncements about what humans will or will not accept may be premature. The propulsion challenge similarly admits degrees of impossibility. Antimatter production rates are currently absurdly low, yes, but they are not zero. We do produce antiprotons. We have stored them for hours. The technology works in principle, even if scaling to interstellar mission requirements seems impossible with current infrastructure. Imagine a future centuries hence, where energy production has advanced dramatically, where fusion power is cheap and abundant, where space-based industry uses resources from asteroids and the outer solar system, where antimatter production facilities orbit the sun, using solar energy to drive particle accelerators orders of magnitude larger than anything on Earth today. In such a future, annual antimatter production might reach grams or kilograms rather than nanograms. Mission durations of decades might be acceptable for cultures accustomed to multi-generational projects. The investment required would still be enormous, but no longer inconceivable compared to total economic output. This scenario requires optimistic assumptions about technological progress and social stability over centuries. It assumes no catastrophic setbacks, no resource depletion crises, no political fragmentation that prevents long-term planning. These assumptions may not hold. History suggests that civilizations rise and fall, that progress is not linear, that capability does not increase monotonically over time. But the possibility exists in principle. The physics allows it, even if practical considerations make it unlikely. We cannot say with certainty that antimatter propulsion will never be developed at scale sufficient for interstellar missions, only that current trends and capabilities suggest it will not happen soon. The deceleration problem might also admit partial solutions we have not fully explored. Magnetic sails provide one approach. Advanced materials might enable solar sails that could partially reflect starlight from Proxima Centauri, providing some braking even without laser assistance from Earth. Plasma magnet concepts propose using magnetic fields to deflect stellar wind, creating drag without physical sails. None of these approaches solve the problem completely. All have severe limitations and remain largely theoretical. But they represent the kind of creative thinking that sometimes produces unexpected breakthroughs. Dismissing them as impossible may be premature when we have barely begun serious engineering studies. The destination's hostility presents the most intractable barrier. If Proxima b truly has no atmosphere, no magnetic field, surface radiation hundreds of times Earth levels, then no amount of propulsion advancement makes it habitable. Humans could reach the planet and still die within weeks or months from radiation exposure that no portable shielding could prevent. But our understanding of Proxima b remains limited. We infer properties from indirect measurements and theoretical models. Direct observation might reveal conditions better or worse than current estimates suggest. Perhaps the planet retains a thin atmosphere that provides some radiation protection. Perhaps subsurface ice deposits could support enclosed habitats. Perhaps the twilight zone between eternal day and eternal night offers conditions less extreme than either hemisphere. We will not know until we send probes to investigate. And those probes need not be crewed. Breakthrough Starshot or similar missions could reach Proxima Centauri within decades, returning data about the planet's actual conditions long before any crewed mission could be attempted. This information would transform the discussion from speculation to engineering, from guesswork to planning based on measured reality. If probe data reveals Proxima B to be utterly hostile, if no prospect exists for even minimal human survival on the surface, then the conversation ends. No mission will be attempted regardless of propulsion advances or volunteer willingness. You cannot send humans to a destination that will kill them within days regardless of what technology they bring. But if the probes reveal something unexpected, if Proxima B proves more amenable to human presence than our bleakest projections suggest, then the calculus changes. The radiation during transit remains severe. The journey time remains decades. The return remains impossible. But perhaps the destination rewards those who survive the voyage with opportunities worth the sacrifice. This is speculation layered on speculation. We do not know what future technology will enable. We do not know what Proxima B actually offers. We do not know how future humans will weigh risk versus reward, or how they will value exploration compared to safety. Making confident pronouncements about what will or will not happen centuries hence requires hubris that history repeatedly punishes. What we can say is that current technology makes crewed missions to Proxima B impossible. Not difficult, not expensive, not risky, but actually impossible in the sense that no plausible mission architecture using demonstrated or near-term propulsion can deliver humans to Proxima B alive and healthy enough to accomplish useful work. This impossibility might be temporary. It might last decades, centuries, or forever depending on how technology develops and what physical limits prove truly fundamental versus merely challenging. We cannot know. We can only work with what we have and what we can reasonably project. And what we have is insufficient. What we can reasonably project over the next century does not include propulsion systems that dramatically change the interstellar travel equation. We might see incremental improvements. We might develop fusion propulsion or more efficient ion drives or improved solar sails. These would enable faster travel within our solar system and perhaps to the nearest stars for flyby missions. But crewed missions that stop at Proxima B, that allow meaningful exploration and possible settlement, remain beyond foreseeable capability. The barriers are too high. The risks are too severe. The benefits are too uncertain. So the practical answer remains unchanged. We cannot reach Proxima B with current technology. We probably cannot reach it with technology we will develop in the next several generations. We might someday develop technology that makes the journey possible, but that someday is distant and uncertain enough that we should not plan around it. Better to focus resources on what we can accomplish. Mars mission, asteroid mining, outer solar system exploration, robotic probes to other star systems. These are achievable goals that advance human knowledge and capability without requiring impossible breakthroughs. Better to accept our limitations than to chase dreams that current physics and biology forbid. Better to work within constraints than to rage against limits we cannot change. Better to achieve real progress toward reachable goals than to fixate on destinations forever beyond our grasp. Proxima B will always be there, for 0.24 light years away, tantalizing us with its proximity and tormenting us with its inaccessibility. We will study it from afar with increasingly sophisticated instruments. We may send robots to investigate if technology permits. We will dream about what it would be like to walk on its surface under the dim red glow of its star. But we will not go. Not in our lifetimes. Not in our children's lifetimes. Not in any time frame where current understanding of physics and biology remains valid. This is the harsh reality that honest assessment demands. This is why reaching Proxima b is impossible for human missions. The distance defeats us. The radiation destroys us. The journey exceeds human lifespans. The destination offers uncertain welcome. The return cannot happen. We can see Proxima b. We can measure it. We can study it. We can imagine visiting it. But we cannot reach it. And this impossibility teaches us something profound about our place in the universe. We are creatures of Earth, evolved for Earth, adapted to Earth's specific conditions in ways so deep that leaving our home world for extended periods damages us at cellular and molecular levels. We can visit space briefly. We can survive in hostile environments with sufficient technology. We can expand throughout our solar system if we invest the necessary resources. But we cannot easily transcend our biological nature. We cannot simply decide to become creatures capable of thriving anywhere in the universe. Our bodies are optimized for one planet, one gravity level, one radiation environment, one set of atmospheric conditions. Departing significantly from these parameters imposes costs that accumulate over time. For journeys within our solar system, these costs are manageable. Astronauts on the International Space Station accept bone loss and muscle atrophy and radiation exposure that exceeds Earth norms. They return after months and recover. Mars missions would push these limits further, but remain within human tolerance for expeditions lasting a few years. Interstellar journeys push past what human biology can tolerate. The radiation accumulates beyond survivable levels. The time stretches beyond single lifespans. The isolation exceeds what psychological health can endure. We hit hard limits not because of engineering failures, but because of fundamental incompatibilities between biological humans and the interstellar environment. This realization should temper our ambitions without extinguishing them. We can still explore the universe through robotic proxies. We can still study distant worlds with telescopes and spectroscopy. We can still expand human presence throughout our solar system. We simply cannot personally visit every interesting location in the cosmos. Accepting this limitation does not mean surrendering to despair or abandoning space exploration. It means directing our efforts toward achievable goals, toward destinations we can actually reach and potentially inhabit. It means investing in robotic exploration for targets beyond our biological reach while focusing human spaceflight on locations within our solar system. It means growing up as a species, accepting that the universe is larger and harsher than our myths suggested, and finding meaning in what we can accomplish rather than mourning what we cannot. Proxima b represents that limit. 4.24 light-years. Close enough to detect and study. Far enough to be forever unreachable by biological humans using any technology we can currently envision. This is not defeat. This is clarity. We know where we stand. We understand our capabilities and our limitations. We can plan accordingly, working within constraints rather than pretending they do not exist. The dream of reaching Proxima b was beautiful. The reality is impossible. And that is the final, harsh truth we must accept. Tonight, when darkness falls, step outside and look toward the southern sky if you live in the northern hemisphere, or toward the north if your home lies south of the equator. Find the constellation Centaurus, the Centaur. Near its brightest stars lies a point of light that most people never notice, never think about, never realize represents our closest stellar neighbors. Alpha Centauri, 3 stars bound together by gravity. 2 sun-like stars orbiting each other every 80 years. And Proxima Centauri, the red dwarf, orbiting the pair at tremendous distance, taking over 500,000 years to complete one revolution around its brighter companions. You cannot see Proxima Centauri with your naked eye. It is too dim, Too small, too cool. But it is there, a mere 4.24 light years away. And orbiting this invisible star is Proxima b, the planet that captured our imagination when astronomers announced its discovery in August of 2016. For a brief moment, headlines shouted hope. Our nearest exoplanet, in the habitable zone, potentially like Earth. So close we might reach it within human lifetimes if we could just develop the right technology. That moment passed when the calculations were completed, when physicists and engineers and biologists examined what reaching Proxima b would actually require, when the enthusiasm of discovery met the cold mathematics of interstellar travel. The distance is too great. Not impossible in some abstract sense, but impossible for beings of flesh and blood, for creatures evolved to thrive within Earth's protective magnetic embrace, for fragile biological machines that cannot survive extended cosmic ray bombardment. We are built for Earth. Our cells expect Earth's radiation environment. Our DNA repair mechanisms evolved to handle the damage rate encountered at Earth's surface, not the damage rate found in deep space. Our lifespans match the timescales of terrestrial existence, not the decades or centuries required for interstellar journeys. Proxima b is not built for us. It orbits a star that lashes its surface with radiation. It likely has no magnetic field to deflect stellar wind. It may have no atmosphere, or an atmosphere of poisonous composition. It shows the same face to its sun eternally, one side baking, the other freezing, with only a twilight band between where conditions might permit liquid water. Even if we could reach this world, even if some miracle of propulsion delivered humans to its surface alive, they would find themselves in an environment utterly hostile to human biology. They could not step outside without radiation shielding. They could not breathe the air if air exists at all. They could not establish self-sufficient colonies without continuous resupply from Earth. And Earth is 4.24 light years away, with signal travel time preventing any real communication. This is the destination we dream about. This is the world that headlines proclaimed as humanity's possible future. This is where we imagine establishing our first interstellar colony. The dream was never realistic. It was always fantasy, wishful thinking that ignored physics and biology in favor of science fiction narratives where human will overcomes any obstacle. We wanted Proxima b to be reachable so badly that we ignored every calculation showing otherwise. Now we must confront reality. We must accept what the mathematics tell us, what physics demands, what biology requires. We must acknowledge that some destinations lie beyond reach not because we lack courage or technology, but because reaching them would destroy us in the attempt. This acknowledgement feels like failure to those raised on stories of unlimited human potential. It contradicts the narrative that sufficient determination and ingenuity can solve any problem. It suggests there are hard limits on what we can accomplish, boundaries we cannot cross through effort alone. But it is also liberation from impossible expectations. If Proxima b is unreachable, we can stop pretending otherwise. We can redirect resources from fantasy projects to achievable goals. We can focus on our solar system, which offers abundant opportunities for exploration and expansion. We can accept our limitations without shame, working within constraints rather than exhausting ourselves against immovable barriers. Mars awaits, difficult but possible. The moons of Jupiter and Saturn wait to be explored. The asteroid belt holds resources beyond measure. Our solar system provides room for growth that will occupy humanity for centuries, perhaps millennia. These are real destinations with real potential, places we can actually reach and possibly inhabit. Proxima b serves a different purpose, not as destination but as limit, not as goal but as boundary marker, not as future home but as a reminder of our cosmic constraints. It sits in the sky, forever visible to our telescopes, forever beyond our reach, teaching us humility. The universe is vast beyond human comprehension. It contains trillions of galaxies, each with billions of stars, many hosting planets where conditions might permit life. The cosmos is filled with wonders we will never see directly, worlds we will never visit, civilizations we might never contact if they exist at all. This vastness is not hostile. It is simply indifferent. The universe operates according to physical laws that care nothing for human desires. It does not design barriers to stop us. It simply is, and we must work within the constraints that existence imposes. Proxima b is our nearest exoplanet neighbor. It is also unreachable. Both statements are true simultaneously. Both must be accepted. Both teach us something about our place in the cosmos. We are not masters of the universe, not destined to spread across every world, not capable of transcending every limitation through technology and will. We are one species on one planet, evolved for specific conditions, capable of extraordinary achievements within our domain, but constrained by biology and physics when we venture too far from home. This is not a reason for despair. This is simply truth. And truth, however disappointing, provides firmer foundation for planning than comforting lies. So we look up at Alpha Centauri, knowing that among those distant points of light lies a planet we can see but never touch, measure but never visit, dream about but never reach. We acknowledge the barrier, accept the limit, and turn our attention toward destinations that physics and biology permit. Our solar system beckons. Let's explore it thoroughly before mourning what lies beyond our grasp. Let's achieve what is possible before lamenting what is not. Let's be grateful for the world we have rather than fixating on worlds forever denied to us. Proxima b shines in the data from our telescopes, a tantalizing target 4.24 light-years away. And 4.24 light-years might as well be infinity for creatures of flesh and blood. The distance is too great. The radiation is too severe. The journey is too long. The destination is too hostile. The dream is over. It is time to wake up and appreciate the solar system we actually inhabit, the planets we can actually explore, the future we can actually build. Proxima b will always be there, visible to our instruments, forever beyond our reach. And that is the final truth, harsh but undeniable, that we must accept. The journey is impossible, not difficult, not expensive, not dangerous in ways courage might overcome. Impossible, absolutely, irrevocably, forever. This is the reality. This is why we cannot reach Proxima b. And this is why we must look elsewhere for humanity's future among the stars. Perhaps centuries from now, humans will look back at this moment in history with amusement or pity. They might shake their heads at our pessimism, our limited imagination, our failure to foresee technological breakthroughs that made interstellar travel routine. They might visit Proxima b regularly, laugh at the barriers we thought insurmountable, wonder how we could have been so wrong about what was possible. Or perhaps they will look back and understand that we were right, that the barriers we identified were real and remain real, that Proxima b stayed forever beyond reach despite centuries of trying, that the universe genuinely imposes limits on biological beings that cannot be overcome through technology alone. We cannot know which future will unfold. We can only work with the knowledge we have, the physics we understand, the biology that constrains us. And that knowledge, that physics, that biology, all point toward the same conclusion. Proxima b is unreachable by human crews using any technology we can currently build or credibly project. The mission would kill its crew through radiation exposure. The destination might kill anyone who survived the journey. The return is impossible. The scientific value could be achieved through robotic missions at far lower cost and zero casualties. No rational analysis supports attempting such a mission. No honest assessment of risks and benefits justifies the expense and loss of life. No ethical framework that values human life permits sending people to certain death for purely symbolic achievements. This is the final calculation. This is what the mathematics tell us when we strip away wishful thinking and confront reality honestly. Proxima b is impossible to reach. Not today, not tomorrow, not within any time frame where current physics and biology remain valid. The harsh reality is clear. The dream is over. The limit is absolute. We must accept this truth and move forward, building a future within the solar system we can actually explore rather than fixating on destinations forever beyond our grasp. This is wisdom. This is maturity. This is growing up as a species and accepting the universe as it is rather than as we wish it to be. Proxima b is 4.24 light-years away, and we cannot reach it. That is the end of the story.